Yeah, hi all. Welcome to this lecture 8 of this lecture series on constraint optimization. Today we are going to look at the convex functions. In last few lectures we discussed about convex sets and we'll now further move on to convex functions and also define what are convex programming problems, why they are useful to us in this unconstrained optimization theory. So before moving ahead, let's recall what we studied in the last few lectures. Uh, we studied convex sets. So what are convex sets? So any set in which if we take any 2 points and the line segment joining those 2 points is also inside the set, then such a set is a convex set. Here in blue color you can see an example of convex set. You can also have a look at some examples which are non-convex, like something like this. So here you can see if I take these 2 points, some of the points on the line segment joining the 2 points are not inside the set. So this is a not convex non-convex set. We also studied a very important lemma called Farka's lemma, uh, which says that let A be a m cross n matrix and C be a n cross 1 vector. Then exactly one of the following two conditions are true, or following two systems has a solution, either this or this. So this says that if a either a x less than equal to 0 and C transpose x is greater than 0, so there would be some x which satisfies these two condition, or uh, if there is no x, then the other condition, that is A transpose y equal to C for all y greater than 0, has to be true. So this is a very important lemma for deriving optimality conditions in optimization theory. Let's look at the geometrical interpretation of Farka's lemma, which we discussed in previous lectures.
ಡೆಸ್ಕ್ಟಾಪ್ ಸಿಸ್ಟಮ್ ಬ್ಯಾಕ್ ಇಲ್ಲ ಈಗ ಅದೊಂದೇ ಇರೋದು ಇನ್ನೊಂದಿಲ್ಲ
So,
ಇದೊಂದಿದೆ ಬಟ್ ಇದು ಕನೆಕ್ಟ್ ಆಗಿದೆಯಾ ಅಂತ ಗೊತ್ತಿಲ್ಲ
so let a1, a2 till am be some vectors, n cross 1 vectors, and let us define A such that these vectors are the rows of the matrix. So for example, let a1, a2, a3 be some n cross 1 vector, and we define a matrix A such that these vectors are the rows of the system. Then let us draw it in the graph like this. So ax less than 0 means all the x's for which, so ax actually means dot product of this a1, a2, a3 with some x is less than 0. So basically it means an area which is shown here in red on the left hand side, an area that is with obtuse angle with all a1, a2 and a3. So basically the red. Now let's say C can be let C be a vector, then C transpose x means dot product of x with C, that is greater than 0. So here this the common area with blue and red shows that an x for which ax is less than 0 and C transpose x is greater than 0. So for this you can see ax is less than 0 and C transpose x is greater than 0. Uh, Either this on the left hand side is true, or C can be uh, inside this hull made by these three vectors a1, a2, a3, and here you can say that C is a some positive linear combination of a1, a2, a3. So y2 a2 plus y3 a3. So as you can see, only one of these two conditions will be true. Either this will be true or this will be true. This is what Farka's lemma says. Actually, you can we will not use Farka's lemma in today's lecture, but we'll use it in the deriving optimality conditions in further coming lecture. But it's an important lemma that we discussed in a previous lecture, so I just wanted to just reiterate it. Now let's come to today's lecture. Let's start today's lecture. Um, and let me start with a diagram. So let there be a function like this. Okay, so and then let there be another function like this. So as you can see, for the function on the left, uh, there is a point, let's call this x star, for which on the right, if we move on the right side of the x star, the value of the function keeps on increasing. And even if we move on the left side, even then the value of the function increases, and it keeps on increase. And this is a unique point. There is no other point in fx like on the left hand side like this. But if you check on the right side, there are multiple points. So multiple points here. So let's call it x1 star, x2 star, for which if we move on both sides, the value of the function increases. There are uh, uh, several points like this. Even though these are so we discussed these points. So these points are called local minima, and they may or may not be equal to the global minimum of the function. That is, the smallest value of a function may not be equal to these values. But if we look at the function on the left hand side, it this point is a local minima, but it's also a global minima because it is the lowest point. So there are there are some special properties in these kinds of functions, and let's look at them. So if we look at some functions like this, let's say, and if we take 2 points and join them with the line, you can very well identify that the value of the function at any points between these 2 points, let's say a and b be 2 points and c be a point in between the two, then fc is smaller than the value of the point on the line. So fc is always smaller than that. You can take any 2 points and this will always be true. Fc will be smaller than this point. Let's call it g. So g will always be greater than equal to fc. Okay, we can have a function like this also. So if we take any 2 points, it's again true. If we take these 2 points, then the function value is equal to the value on the line. So such functions are called convex functions. So the functions in which if you take any 2 points and join a line and make a line between those 2 points, then the value of the function is always less than the value of that line. So that is the definition of convex functions. Now let's define it formally. I just gave you an idea of what convex functions are. So convex functions. So let C be a subset of some real space, be a convex set. So remember, we are trying to define convex functions and we have taken a convex set. Now a function f from C to R is said to be convex if any x1 comma x2 belongs to C, that is any 2 points x1 x2 on C, and some lambda belonging to 0 and 1. So lambda will be used to define that line. The following is true. So f lambda x1 plus 1 minus lambda x1 is less than equal to lambda fx1 plus 1 minus lambda fx2. If this is true, then the function is convex. So this is actually this definition is saying what we discussed previously. Let me reiterate that. Um, so let A and B be 2 points and C be any point between them. Okay. Then this point C comma FC will always be lower than this point for convex functions. So as you can see, this point is represented by this, and this the green point at the bottom on the function is represented on the left hand side. So this inequality, whenever it suffices, then it's called so the function is called convex function. Now there's something called strictly convex. So where this inequality, the equality sign in this inequality is gets removed. So so those are called strictly convex. So for example, if I have something like this, where the bottom at the bottom all the points have the same value, then this is not a strictly convex function. It's a non-strictly convex function. On the other hand, if I have a parabola like this, it's a strictly convex. So if I draw any two line, uh, I take any 2 points anywhere, the line will always be above the function. Whereas here, if I take these 2 points, the value of the function and the line is equal. So this is not strictly convex. So this is just a variation of convex function. I'll just write it here. I'll not formally define it because it's fairly obvious. So non-strictly convex. So the example I gave you is in like one dimension, like C belongs to R1. What happens if R is 2? So let's say we have two variables x1 and x2. So this is you can see that if we take any 2 points on this and draw a chord, then that chord is always above the function. So this is also a convex function here. So yeah, so this is an example of a convex function here again here. Um, now just how we define convex functions, we can also define what are concave functions. So concave function. So let me just define it formally, then I'll explain it. Let C be a subset of some real space Rn, be a convex set of function f from C to R is said to be concave if and only if minus f is convex and is said to be strictly convex if and only if minus f is strictly concave. Sorry, is called strictly concave if minus f is strictly convex. So it's fairly obvious. For example, I think you would have understood it by now that this is a concave function. As you can see that if this is f and if you want to plot minus f, it will be something like this. And we know this is a convex function, so f is a concave function. Uh, this is a definition of concave functions. So why we are discussing concave is like sometimes in optimization there is minimization problems. So minimization of fx, and it is very helpful if f is convex because it 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 always has it all the local minima in of fx is also the global minima if f is convex. But sometimes the problems are like maximizing problems. So for them, for if their f is concave, then we can simply change it to a minimization problem of minus of fx. These two values are same. So we can change the minimization problem, and we know that minus fx is convex if fx is concave. So that's why concave functions are useful in this sense. So now we have discussed the convex and concave functions. Now let's discuss some functions which are neither. So for example, a function like this is neither concave nor convex. So neither concave nor convex. Correct. So this is the definition of concave and convex. Now let's look at some examples of concave and convex functions. Yeah, so examples. Let's say the first example is um, A transpose x plus b. So basically a linear function where x like x belongs to some Rn, which makes A also belongs to some Rn and B is also belongs to Rn. So fx is this function. Uh, can you tell me what will this represent graphically? So let's restrict ourselves to one dimension right now, n equal to 1 for the example sake. Uh, can you tell me what will this represent? Okay, so this will represent a line not passing through origin if b is not equal to 0. So this is x and this is fx. So this is what this means. And you can see this is an affine function. We discussed affine function in our last lectures. Affine function is a oh sorry, affine set. So affine set is a set in which if we take any 2 points in the set and make a line joining the two. So line, not line segment. We pass a line. The whole line, if lies inside the set, then that set is an affine set. So that what affine set means. So yeah, so I was asking what fx equal to A transpose X will represent graphically. So that's what I was asking. So it represent if n equal to 1. So it will represent a line. If we increase the dimension of the of n, let's say n equal to 2, 3, or so on, it will represent a hyperplane in higher dimensions. So yeah, so what is this? Is this a convex function or a concave function? What do you think? This line.
Convex.
Yeah, it is convex because if I take any two, uh, if I take any 2 points and join the line, the function value, the value of the function and any point on the line is same. So it satisfies the definition of convex functions. Yes, so it is a convex function. But what about concave? So let's check minus f for a second. So minus A transpose X minus B. What does this represent? Actually, this also represents a line with negative slope and negative um, negative y coordinate, you can see. So let me represent this using some line. So it will be somewhere here, something like this. And this is also convex. So if I take any 2 points and join the line, then the value of line and the function are equal at each point. So uh, we can call it less than equal to. So it's not strictly convex, but it is convex, this line also. And now if f is convex, what does it make? What can we say about f? Which means f is concave. So actually this line is both convex and concave function. And this is the only line. So any line or a hyperplane in high dimension is both convex and concave. And this is like a unique thing. So no other type of function is both convex and concave apart from a function like this. So yeah, it's both concave and convex. Now let us look at one other example. Uh, fx is equal to e to the power ax, where a belongs to real number. Let's say some real number, and x belongs to R also. So x is also a of single dimension variable. So let's first draw its graph. Let's take a greater than 0. Let's say a is greater than 0. So then its graph will be something like this. It's a monotonically increasing graph. And if I take any 2 points like this, if I take any 2 points, the line is always above the function at every point. You can go infinitely in the negative or in the positive. This will always happen. So this is convex function. And it turns out that it is strictly convex. You'll um, eh, like you'll never find any 2 points for which the line is exactly coinciding the function. So you'll never find that. So it's actually strictly convex. Now let's look at the function for a less than 0. So I'll just copy this diagram. Yeah. So for a less than 0, the function will be like this. Sorry. Okay. And what do you think this is? Convex or concave? Should the sign change in a will make it concave? Um, so let's check it. So let's say we take 2 points and we join the line. It's again above the function. It will always be. So um, this is also convex, and by the same logic, it's also strictly convex. So actually, e to the power ax is convex, irrespective of the sign of a. Uh, However, if we take minus f, minus e to the power ax, uh, that will become concave because the function will be something like this. So this is a concave function because the line joining the 2 points is below the function. So this is a concave function, minus fx. This is minus f here. So yeah, so this is a convex function. Now let's look at inverse or of a function which is concave. Let's say I'm I want to give you an example which is concave. So let's say we look at log x. So log x has a graph something like this, and if I want to check through that point thing, if I take 2 points, draw a line, it's below the function. So this is a concave function. Log x is a concave function, and it's a good example of a concave function. Now let's look at a function x cube. So I'll draw and tell me what it is like. So I'll draw the graph. So it is something like this, right? So is it convex or concave? Tell me.
Half concave, half convex.
Yeah, yeah. So if I define the domain to be positive, so let's say I take f only from r positive to r, then this is uh, convex function. If I take it reverse, let's say r negative to r, then it's a concave function. But if I take the domain to be R, then I can't say anything. So it's neither concave nor convex. So depends upon what domain you take. So yeah, so if the domain is all positives, then it is convex. If it is all negative domain, then it is concave. And if it is the whole space R, then it is neither convex nor concave. So because we discussed such a functions earlier, right? So it can be possible that a function is neither convex nor concave. So yeah, it comes in that category. Now there is one more special, not special, but a function that I just want to tell you whether it is a convex or concave. Let's say this is a function. So its graph is like this. Uh, yes, the graph is like this. So Yeah, so yeah, this is very easy, I think. So what do you think it is?
Convex.
So this is convex function. So the reason I gave you this example is because uh, a convex function has nothing to do with its um, differentiability. So it's not differentiable here, but it doesn't matter. So we just have to look at the definition. This is a convex function. So sometimes people have a think of when they think of convex, they think of smooth functions like parabola or something, but it has nothing to do with that. A convex function is nothing related to differentiability. It's just that, and if you take any 2 points, um, and the line joining those 2 points should be always the values of any point between those 2 points. The function should be smaller than that line. That's it. That what convex function means. So yeah, so let's end these examples here and let's move on to uh, let's move on to the next topic, which like before getting into the mathematical aspects of the usage of convex function, defining convex programming problems, let's define why convex functions are so useful. Why are we looking into them so much? So it turns out that most of the it's a very useful function used in optimization theory, and the reason is that it's global. If all the local minimums of the convex function is their global minimum as well. So let me just define it properly. So let X be a subset of real space Rn and F be a function X from R. Now consider the optimization problem. Consider the optimization problem, minimization of fx such that or subject to x belonging to x. So basically it's a constrained optimization problem. We want to minimize the cost function fx where such that x belongs to some set x. Now we already discussed in previous lectures what are global minimum and maximum. I'll just write their formal definitions here. So if there exists x star belonging to x such that fx star is less than equal to fx for all x belonging to x, then x star is global minimum of f over x. So basically what this statement is saying that if there exists, so this symbol is there exists, is just a English, you read this in English as there exists. If there exists a x star in x, so there is a point x star in x such that the function value at that point is smaller or equal to all other function values for all x in x. So for all the x's, then x star is a global minimum. So this is fairly obvious definition that a point where function value is smallest is called global minimum. A similar definition, mathematical definition, is that x bar is local minimum of f over x if there exists a delta greater than 0. Delta is a small real number such that fx bar is less than equal to fx for all x belonging to x. If x belonging to x, then it is global, but this time we'll write intersection of ball of radius centered at x bar and radius delta. So this is the definition of local minimum. So let's just read what this means. So x bar is a local minima of of f over x if there is a small number delta greater than the positive number delta such that function value at that point x bar is smaller than all other x's such that x belongs to x intersection some ball of radius delta centered of x. So this is just a neighborhood of x. So let's say this is x bar, and if we check only in the, so let's say this is my set x, okay, and I just want to check in the nearby in the delta. So this area, this neighborhood, this is called neighborhood of x bar, and this radius is delta. So this is this ball of radius r. This is what I mean by ball of radius r and centered about x bar. So I don't care about whole of x. If it is just smaller in that particular region, it is local minimum. And if it is smaller in all whole of x, then it is global minimum. So that's what global and local mean. We have already discussed this. I just wanted to just reiterate these two definitions because these are important. So one important property that convex functions have, which is the reason why we are studying it, is if f is a convex function and x is a convex set, then every local minimum of one that is that optimization problem, let's call this one, this optimization, every solution of every local minimum of optimization problem 1 is a global minimum. So this is an important property that convex set and convex functions have, that if we have a convex function which we want to minimize over a convex set, then every local minimum is a global minimum. And we discussed earlier, global minimum is difficult to find, but we have methods to find local minimums. So if a function is good, like sometimes it's called a good function, like if it is convex function and set over which we want to uh, find x, set over which we want to optimize x is also convex, then local minima is enough to find the global minima. So this property makes us interested in convex functions and convex sets. So that's why we are studying convex functions. Now, similarly in this regard, because this theory, this property is true, that we call these kinds of problems by a name called convex programming problem. So let C be a subset of some real space Rn, be a non-empty and convex set. Let it be a convex set. And f from C to R be a convex function. Let's assume this too. Then convex programming problem is given by minimization of x subject to x belonging to C. So this is called convex programming problem. Let me just Okay, so this is a special class of programming problems called convex programming problems, in which the function we are minimizing is convex, or the set over which x is constrained is a convex set. Also, one more thing I want to just iterate here or write here is, if f is concave and we want to maximize fx, then we can always convert it into minimization problem like this. Okay, so maximizing fx where f is concave can be written as, I mean, f need not be concave to write this. This is always true. So maximization of fx is same as finding negative of minimization of minus fx. This is always true. But the thing is, if f is convex, the concave, this becomes convex, and this is actually same as the convex programming. This can be become made into convex programming problem. So minimization of fx if f is convex, or maximization of fx if f is concave, are both class of convex programming problems. Okay, so yeah, so that is that. Um, now let's iterate two theorems. I think we are less on time, so I'll just state the theorems. I'll maybe upload a proof later on. The proofs of these theorems are easy, but because we are running out of time, we'll just state the theorem and maybe one more definition of epigraph. So uh, yeah, and then we'll end the lecture. So first theorem is same we have already discussed it many times, that every local minimum of a convex programming problem is a global minimum. So this we have already discussed previously. I'm just stating it as a theorem, and I'll skip the proof here, but I'll upload it later. I think I'll do that. So what this is saying, let's say we have a set C. Let's say we have a set C, and we find a local minima x star in this. So local minima means that in the neighborhood, yeah, in the neighborhood, in this neighborhood, yellow neighborhood, uh, that is delta. Let's call it delta. Uh, delta neighborhood of x star. At x star, the function value is the minimum in that yellow region. But we want to, this is given, and we want to prove that this x star is minimum in whole C if C is convex, and as C is convex set, and F is convex function. These two things are given, and it's also given that x star is a local minima. That is, it is at x star, fx star is minimum in this delta region. So we have to prove that this f at x star f is minimum for whole C. That we have to prove. So the way so you can try it on your own if before checking the solution. But the way we can do it is, uh, so we'll take 2 points. So because for convex function everything is like related to line as such, so we take 2 points, make a line. So from that idea, you can take 1 point outside outside this delta region, but inside convex set C, and 1 point inside this delta region. Join this line and try to use the conditions on this. So let's call this point Y, let's call the point Z, and try to write the relation between x star z y, and you may be able to prove this theorem. So yeah, so I'll upload the proof later. The second important theorem is the set of all optimal solutions to the convex programming problem is convex. So, so what this is saying, that let's say we have a convex programming problem, that is minimization of fx, where fx is convex function subject to x belonging to C, where C is convex set. If this problem is there and we have to find the solution, then let's say there is a set S, and let's say x star belonging to S, and x star is less than or equal to fx for all x star belonging to S and x belonging to C. So basically what this is saying, that if I take x star from set S and uh, any x from C, the domain of the function, then the value for function is x star is less than all other values. So basically set S is a minimization set. So in this set, the function achieves its minimum. So it's not a unique point, it's a set here. So what this theorem is saying, that S is necessarily convex. It has to be convex if we find an optimal set. So this is a so yeah. So these two theorems are important. I'll skip the proof of this two in this lecture, but I'll probably upload it later. Um, upload it later. So yeah. So proof I'll upload later. Um, yeah. Now we'll discuss one more definition called epigraph, and then we'll end the lecture. So epigraph, let X be a subset of real space Rn and f be a function from X to R, and let us describe f using graph. So describe f by its graph. What mean by graph? So the way we draw our graph of fx, so x comma fx, we have to plot x belonging to x, and this should be a subset of Rn plus 1. So any curve fx, and if we plot it, it's actually a subset of a higher dimension, right? So yeah, so that is the thing. So let's say we do that. So for example, something like this. So let's say we draw, this is fx, right? So x is a single dimension, while x comma fx is a two-dimension thing. So that's what it wants to say. Let's have two graphs like this, right? So let this be x, set X. Okay. Then the epigraph of F, represented by EPI bracket F, is a subset of Rn plus 1 and is defined by X comma Y such that X belonging to X, Y belong to R, and Y is greater than equal to Fx. So everything above this graph is epigraph. So everything above this graph and here also inside X is the epigraph of F. So this is what it is, and this like epigraph we have something called hypograph as well, so which is below it. So this is hypograph. Let's write it hypo x fx. Okay, so we'll look in the next lecture why epigraph is important and how it is used to characterize the convex functions. And I'll also the lecture ends here. I'll upload the proof of the theorem, the two theorem that I discussed later, and you can look at it. And if you have any questions, you can ask me. Thank you.